Hello, Professor Sargent here with you again. We're going to take a look at solving linear programming problems by something called the Simplex method. It involves using matrices. Now, I've shown in some previous videos some things that can be done using either a TI-84 or using Excel for performing row operations on a matrix. I'm not going to focus on that in this, but hopefully I'll be able to film another example and get into that some more again on that. It is my belief that the attention should be on what row operations need to be performed, and then getting down into the nitty-gritty of the arithmetic that we can use technology to help us out with that. But not everybody takes that point of view. All right, so the standard maximization problem is one where the objective function is to be maximized and your variables are non-negative. You have non-negativity constraints, and then you're going to have linear constraints where each one has the expression on the left less than or equal to a non-negative constant. And we have actually seen one previously in my video on solving an example by the method of corners, which was followed up with some examples regarding sensitivity analysis. Since we are going to use matrices, matrices are set up with that right-hand column following the augmentation bar. You have equals, not an inequality. So what we're going to have to do is add a non-negative number so that if A is less than or equal to B, A plus C equals B. We're going to call these non-negative numbers that we're adding to turn these inequalities in the constraints. We're going to call them slack variables. And that can represent how much of a what's available, like how many labor hours you have available. Maybe they're not all being used when you get to the optimal solution. So, although we see in the linear programming problem, first, what we're maximizing, the objective function, that's actually going to show up at the bottom of the matrix. So what we do is on that, subtract everything over to the same side as the positive 1z, so that we're left with 0 on the other side. That'll show up at the bottom of the matrix, or simplex tableau. Add a slack variable on the first constraint, add a different slack variable on the second constraint, and I'm not going to be able to show the augmentation bar in what I have following here, let alone this that separates off the objective row from the rest. Just going to see a matrix. So we've turned that, what I have at the bottom there, into a matrix, i.e. the initial simplex tableau. And the rule is to look at the objective row for negative entries and which one has the greatest absolute value, i.e. what's the most negative. And in this case, it's the negative 15. That's going to give us our pivot column. Now we also need a pivot row. And the way we do that is we look at ratios of what's on the right-hand side divided by the corresponding entry in the pivot column. So we have 360 divided by 4 is 90 versus 300 divided by 1 is 300. You go with the least positive ratio there. 90 is less than 300. So I've circled row 1. I have to turn that 4 into a 1 and then use that 1 that we'll have right here to turn this into a 0 and this into a 0. So in other words, this unit column that we see right here is going to get replaced by a unit column over here looking the same, but we're going to be changing a lot of the rest of the matrix. However, what we do should not mess up the unit column here or here. So I'm going to multiply everything in row 1 by 1/4, so that not only I have a 1, but I'm multiplying everything else by 1/4 as well. Once I have that, I would add -1 times 1 plus 1 would equal 0 here. But again, I have to do that to the whole row. So once we've done the first step, -1 times row 1 plus row 2 to give us a new row 2. And since we have a -15 down here, 15 times 1 plus a -15 will give us 0. But again, we have to do that to the whole row of 3. So 15 times row 1 plus row 3 will give us a new row 3. And once we've done this, we will have, first of all, there's multiplying everything in row 1 by 1/4. Next, we're going to take -1 times what we have in red here times -1 times what we have in row 1 plus what we have in row 2. And finally, 15 times what we have in row 1 added to row 3. So now we have that unit column. We begin again with round 2. Are there any negatives in the objective row? And there are. There's only one, so column 1 is going to be our pivot column. We'll come back to that in a moment, though. What we have there can tell us about a feasible solution. The fact that we have a negative still in the objective row means it's not the optimal solution, but we can read this for a feasible solution. We can read that because of this unit column, that was for x sub 2. Read over to the right-hand side, x sub 2 is 90, but there's still some slack. S sub 2 is 210. The rest of the values there, if you don't have a unit column, x sub 1 and s sub 1 are going to equal 0. So far, we've bumped z up from 0 to 1350. In fact, let me back up a little bit here. You can plug in the 90 for x sub 2 to see we're getting z is 1350. And 0 plus 4 times 90, that is 360. 0 plus 90, that's less than or equal to 300, but s sub 2 was equal to 210. So 0 plus 90 plus 210 equals to 300 there. So as I said, since we still have a negative in the objective row, there's more work to do to get to the optimal solution. And we're going to, again, look at ratios of 90 divided by 1/4 and 210 divided by 7/4. Now, you can take out a calculator, you can convert back to fractions if necessary, but 90 divided by 1/4 is the same as 90 times 4, so 360, and 210 divided by 7/4 is the same as 210 times 4/7. 7 into 210 is 30. 30 times 4 is 120. So we're comparing 120 to 360, and 120 is the least of those positive ratios. So here is our new objective row. We're going to turn that 7/4 into a 1, and that's going to be by multiplying by 4/7. Going to multiply all of row 1 by 4/7 to get a 1 there. And then we'll take -1/4 of row 2, add it to row 1, so that we have a 0 here. And 25 quarters positive times the row 2 we get once we have a 1 there. Multiply it by 25 quarters and add it to row 3. So here we go. Multiplying by 4/7 to all of row 2 so that we have the 1 at the pivot entry. Going to multiply all of this now by -1/4 and add it to row 1 so that I could have a 0 there. And multiply row 2 by a positive 25 quarters and add it to row 3. Now that we have no more negatives in the objective row, we know that we're done. We are at the optimal solution. Reading where the unit columns are, in column 1, we have that's for x sub 1. There's a 1 in the row 2. So x sub 1 is 120. Column 2, we have a unit column, and the 1 is in row 1. So x sub 2 is 60. No unit columns for s sub 1 and s sub 2, the slack variables. Those are 0. And then we still have a unit column here for z. Z is 2100. You could, again, go back to the very beginning. So x sub 2 is 120 and x sub 2 is 60. All right, so 10 times 120 is 1200, and 15 times 60 is 900, adding up to a total of 2100. 120 plus 4 times 60, that's 120 plus 240. That's exactly equal to 360. 2 times 120 is 240. 240 plus 60, that's 300. No surplus here. And so our optimal solution, the maximum value of z is 2100, and that was produced by x sub 1, comma x sub 2 equals 120, comma 60. Hope that helps. I'll see you in the next one.